Now that we have this set up, I now want to talk about what I really want to talk about was this the cohomological interpretation logical interpretation of the Riemann zeta function of zeta s. So this is the Riemann zeta function. Okay, so let me just give you a definition. So zeta hat of s is going to be defined to be zeta of s pi to the minus s over 2, gamma of s over 2, 2 to the minus 1/2. Okay, so this is kind of a normalization factor coming from certain regularized products. This part here gets rid of the trivial zeros of the Riemann zeta function. So the trivial zeros are at the negative even integers. Okay, so let me give you a theorem now about this guy. So this theorem is due to Deninger and Soleil and Schroeder. And this is in 1994. So the theorem that they proved is that this guy here is equal to this regularized product of, so now we have this function here, okay. So here, this is the regularized product of this is a product over zeros of the Riemann zeta function. So these are the non-trivial zeros of the Riemann zeta function. And then we have these two factors here. Okay. So we're going to take a little break from this for a second, and then we're going to come back to this. I want to explain how this looks like it's coming from cohomology. So let's recall the strategy for proving the Riemann hypothesis for varieties over finite fields. And this strategy involved what was called a Cohomology theory. All right. So what was a Cohomology theory? So what we had was we were looking at schemes over this finite field. So Q is a power of P, and we were looking for a contravariant functor to graded commutative rings, so over a field of characteristic 0. So this actually takes projective schemes in characteristic P to graded rings in characteristic 0. So here we're going to associate to this a cohomology theory. And by this we have a direct sum, and the direct sum is over the integers here. By graded commutative, we mean that alpha times beta is equal to -1 to the degree of alpha times the degree of beta times beta times alpha. And when we actually interpret this, this will be the cut product in cohomology. Okay, so again, they conjectured this, these axioms that I'm going to write down, and but Grothe and Dieck made this precise. So let me make a little division here. So the first thing that this cohomology theory has to satisfy is finiteness. So this thing is hi of x is finite dimensional. So it's a finite dimensional K vector space. K is in characteristic 0. So it has some vanishing. Okay, so this means that the cohomology is going to be equal to 0 when I is less than 0 or I is greater 2 times the dimension of x. Okay, so another property we have is this Poincaré duality. So Poincaré duality says that there is a perfect pairing. Oh, sorry. Well, yeah, so let's see this. hi of x, h2 to the n minus I of x goes to k. Okay, and what it does, it takes alpha and beta. So there's a perfect pairing. Okay, so to the trace. So there's actually a trace map. In addition, there's a trace map from top cohomology to so n here is the dimension of x. Trace of alpha times beta. Okay, so this goes from here and this is here, and so this is a perfect pairing. Okay, so there's a Kunitz formula, which is another isomorphism like this. It says that the Kunitz formula says that h bullet of x cross y is isomorphic to, so the graded rings of the product is the product of the graded rings, and so you have to, so yeah, you have to define what the product of a graded rings is. So graded rings are. So you have to sum up the graded pieces appropriately to get the graded piece of a tensor product. Okay, in addition to these axioms, there is there's two other conditions. So there's some compatibilities. Right? And then there's some Lefschetz axioms. So these are maybe there's this hard and weak Lefschetz property, and there's a cycle map. Okay, talking about these is like a black hole of conversation. We could talk about these for a very long time and go blue in the face. So the important thing to get from this is that, and maybe I'll do a video of this one time, is that from here we get the Lefschetz fixed point theorem. Okay, from these compatibilities. From here we get so this is what delete. Okay, so if you have the hard Lefschetz property, you can prove the Riemann hypothesis for varieties over finite fields. Deninger actually proved the Weil conjectures and then proved this. So okay, but there's other. Okay, I'm just going to leave it at that. In what we're going to say in the future, these are going to change a little bit, and then these become a little bit more mysterious. All right. So let me go back to our cohomological interpretation of this, and we will come back to this in a moment. So here we are, and now I'm going to kind of recall the strategy for the strategy for the Riemann hypothesis for varieties over finite fields. Okay, so we're going to write the zeta function for varieties over finite fields. Okay, let's say that x, so here we're just going to write it like this. So we have a product from W is equal to 0 up to 2 times the dimension of X of a determinants. So 1 minus TF W negative 1 to the W. Okay, so if I've done things correctly, okay, so what plus 1, I think. Okay, so the even stuff needs to be in the denominator and the odd stuff needs to be in the numerator. Okay, so we have this alternating sum. In the case that for curves, so it's one-dimensional, this becomes FH1. Okay, let me say something else about the Frobenius here. This F 1 minus TFH2. Okay, so this comes from the Weil cohomology theories in the Lefschetz formula. Okay, so the trace formula. So what I want to say is that this Frobenius, this is what I wanted to say, the Frobenius here, okay, so for varieties over FQ, there's a Frobenius that's always acting, okay? And this Frobenius, since we have the Weil cohomology is functorial, it induces an action on cohomology, and then you can look at, say, the characteristic polynomial of this, or this modified characteristic polynomial. Okay, so so what Deninger's strategy is here, this looks very similar like this. So we're going to want this to look like determinants, but we need to modify the cohomology theory that we're going to use. And I'm going to do that now. Now I'm now going to describe Deninger's cohomology theory. So this now is Deninger. Okay, so now we're not going to actually have schemes. There's going to be something crazy going on. This here is replaced by schemes. So we need some other category. So in Deninger's theory, to each projective scheme, and this could be an arithmetic scheme, we're going to need to associate a site, a different site. Okay, and this site could be considered as schemes over F1. It doesn't necessarily need to be a site. It could be something else, right? Like Weil cohomology theories, there's probably lots of different ways to do this. Here, we're going to have graded commutative rings over the complex numbers, not over K now. Okay? These axioms are pretty much the same, well, except for this one. It's no longer finite dimensional. This is going to be a Fréchet space. And so this is a Fréchet space. So these are function spaces. So infinite dimensional vector spaces. Okay? The vanishing is still going to hold. There's still Poincare duality, and there's still a Kunitz formula. There's going to be a much more complicated version of these compatibilities and Lefschetz axioms, which at our level of precision, we don't need to talk about this right now, but maybe I'll talk about this later if I'm like feeling like it. Okay, in addition to these properties, we're going to have some new properties. Okay, so as I said that there was a Frobenius acting on varieties over finite fields, these sites associated to schemes or Arikhelov schemes are going to have a real action. So these are some new things. So there's going to be a real action of, so there's going to be, and this is going to be acting on elements of here. Okay? And so this is what's going to be replacing the Frobenius. And so then there's going to be a Hodge star operator. So the Hodge star operator goes from hi to h2n minus I. So n is again the dimension of x over f1. And this Hodge star operator is going to lead to an inner product. And this thing is going, so this is now, here, this is, now it's going to have some complex conjugation involved in it. Okay? I guess one last thing I should say is that these Lefschetz axioms, these are related to the new Lefschetz axioms, the new versions. So for the Deninger cohomology theory, these are related to the so-called explicit formula. For the Riemann hypothesis. And so these explicit formula are the things that you get, things that you use in order to prove the consequences about the prime number theorem. Okay, let's go back to our cohomological interpretation of the Riemann zeta function. Okay, so let's go back here. From the real action, and let's call this phi on the object. So this is going to be a zeta function associated to some compactification of the integers, or spec of the integers. So to the real action, we're going to have some infinitesimal generator. So theta is defined to be equal to, so the limit as t goes to 0 of phi t star minus the identity divided by t. And so this thing is going to act on this cohomology theory of Deninger. And since it's a derivation, it's since it's an infinitesimal generator, theta is a derivation. Okay, so now Deninger's conjectures are that this thing is actually one of these regularized determinants. So that this thing is actually looks like this. S minus theta over 2 pi on H0. Exactly like in the Riemann hypothesis for varieties over finite fields. Now we have this interpretation, this cohomological interpretation of the zeta function for varieties over finite fields. Given this formula here, we have some expectations. What do we expect? So we expect theta to act as 0 on H0. We expect theta to act as the identity on H2. And then, given all the complicatedness of the zeros, the non-trivial zeros of the Riemann zeta function, we expect theta to be crazy on H1. Okay, so also in addition to this, in order to prove give the conditional proof of the Riemann hypothesis, we need to assume that theta and the Hodge star operator commute. Okay, so I'm going to refer to this in the cohomology theories as Deninger's conjectures. We are now going to give Deninger's conditional proof of the Riemann hypothesis. So here's the claim. Assume Deninger's conjectures. One, define this operator A to be equal to theta minus a half. Okay? This thing satisfies this antisymmetric condition. Two, if you have an antisymmetric operator, this implies that the eigenvalues of A are purely imaginary. And the third thing that we claim is that this implies that the eigenvalues of theta have real part equal to a half. This proves the Riemann hypothesis, since we've cooked up the situation so that the eigenvalues of theta are equal to the zeros of the non-trivial zeros of the Riemann zeta function, or the zeros of the regularized Riemann zeta function. So let me give a proof now. So assume f and g are in H1. Okay, then we can take the cup product of f with the Hodge star applied to g. This is an element of H2, so theta acts as the identity on H2, so we have this equality here. Theta is a derivation, so this is this. And we also know that theta and the Hodge star commute, which gives us this formula. Taking traces, we have that the inner product of f and g look like this. The inner product with the derivatives like so. And now we can manipulate this expression. So we're going to break up this into two pieces, two halves, and I'm going to subtract this over to the other side. So this tells us that 1/2 fg minus f theta g is equal to theta f g minus 1/2 fg. Well, this side here, this is equal to f, and then we have 1/2 minus theta applied to g. And this side here, well, this is equal to theta minus 1/2 f g. Or, in the terminology that we gave, the notation that we set up before, this says that AFG is equal to negative FAG. And this proves this antisymmetry. So now I'm just going to recall this basic linear algebra and conclude the proof. Okay, so suppose that we have AU is equal to lambda U, so we have U is an element of H1, and U is not equal to 0, then we're just good to check that lambda, absolute value of U squared, so this is equal to lambda U, like so, and this is equal to AUU, right, since it's an eigenvalue. And now the skew symmetry comes in, and this is equal to negative U, and now we have lambda U, and this is negative lambda bar U squared. So now this uses the fact that we have this inner product, and now where the complex conjugation gets involved. This implies that lambda plus lambda bar U squared is equal to 0, or is equal to 0, which implies that 2 times the real part of lambda is equal to 0, which implies, of course, that the real part of lambda is equal to 0. So lambda is purely imaginary, as we wanted. So the final part, so suppose that theta u is equal to lambda u. Then 1/2 plus lambda, or 1/2 plus theta of u, so this is A. So A is okay. So let's redo this. Sorry, I made a mistake there. So suppose this, then take theta minus 1/2 of u. So this is equal to lambda u minus u over 2, which is just lambda minus 1/2 over u. Okay, so now this tells you that lambda minus 1/2 is, this is an eigenvalue for A, so this is A of A, and this is an IR. So this tells us that lambda is an element of 1/2 plus IR. Okay, this concludes the conditional proof of the Riemann hypothesis.